Hello, and welcome to my videos and to my YouTube channel, which is called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. In this video, I will assume that you are familiar with the statistical concepts listed here. Alpha, the significance level, P, the p-value, critical value, test statistic, and specific test statistics, Z, T, and chi-square. These are all covered in articles in the book and in previous videos. I will also assume that you have read the Part 1 video on confidence intervals or read that article in the book. This video is the 8th video in a playlist on central concepts in inferential statistics. The video is called Confidence Intervals, Part 2 of 2, Some Specifics. See statisticsfromatoz.com/videos for the latest status of my videos completed and planned. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This will give you the overall picture of the concept on a single page. After that, we'll go into a detailed explanation of each of the keys. For this video, there are 4 KTUs. Here is the first key to understanding. Normally, a KTU is a statement, and the other KTUs in this video are statements. But here we need to provide the purpose of the test and the confidence interval formulas for 4 different test statistics. So a table like this one is a good way to organize this information. It shows the formulas for estimating the mean, the proportion, and the variance using the test statistics Z, T, and chi-squared. KTU number 2 says, the form of the output of confidence interval analysis varies with the type of analysis, for example, regression or a t-test, as well as the type of software. Key number 3 says, confidence intervals which do not overlap indicate a statistically significant difference. The converse is not always true. Key to understanding number 4 says, for processes, use confidence intervals only if control charts show that the process is under control. And here on one page are all 4 keys to understanding specific concepts of confidence interval, which we'll cover in this video. You may wish to pause the video at this point and read them all together. Okay, now let's take a closer look at each key to understanding. KTU number 1 is a table which contains a lot of information. It gives the most common formulas for calculating confidence intervals. On this slide, we show the column titles and the first 2 content rows of the table. These show 2 confidence interval formulas for the mean, 1 formula for Z and 1 formula for T. These are 2 test statistics commonly used for the mean. A statistic is a numerical property calculated from sample data, and a test statistic is one which has an associated probability distribution. Z is the test statistic whose distribution is the standard normal distribution. In the Part 1 article in the book on confidence intervals and in that video, we use the test statistic Z to illustrate the concepts because Z is somewhat simpler to use than T. There is only one Z distribution, which is the standard normal distribution. But Z has its limitations. It should only be used when we know the standard deviation, sigma, of the population or process, or if we believe we have a very good estimate of it, and when the sample size n is large enough, say when n is greater than 30. Some experts recommend n greater than 100. For the test statistic T, there is a different distribution for each different value of the sample size n minus 1. Use T instead of Z when population standard deviation is not known or when the sample size is small. Since Accuracy suffers when sigma is not known. The confidence intervals calculated with t are wider than those calculated with z. That is, their margin of error is larger. This is the bottom part of the table in KTU number 1. It shows the formulas for two additional purposes. Those are for estimating proportion and for estimating variance. For proportion, the test statistic z is used again. For estimating variance, the test statistic chi-squared is used. Key to understanding number 2 says, the form of the output of confidence intervals analysis varies with the type of analysis, for example, a regression or a t-test. And the form of the output also varies with the type of software used. This slide and the following slide will give some examples. Here is an example of confidence intervals calculated for the mean and for the median. Here is an example of a multiple linear regression analysis. The right half of this table has 4 columns which give upper and lower confidence bounds. These define the boundaries of two confidence intervals. If we select alpha equals 1%, then 1 minus alpha equals 99%. The two rightmost columns show the lower and upper confidence bounds for those confidence intervals. For the rows, intercept, and the 3 variables, house size, bedrooms, and bathrooms. If we select alpha equals 5%, then 1 minus alpha equals 95%, and the two columns lower 95% and upper 95% show these confidence bounds. Here are 2 examples of outputs from different statistical software. The first is from a 1-sample t-test. The second is from a 2-sample t-test. In the first example, we are analyzing the variable pulse. The sample mean was calculated as 78.73. The 95% confidence interval column heading tells us, first of all, that alpha equals 5% was selected, and thus a 95% confidence interval was calculated. Its boundaries are the confidence bounds 75.55 and 81.92. In the second example, we see output produced from a 2-sample t-test using different software. A table is provided which compares statistics for Furnace 1 and Furnace 2. Below the table, we see that the test estimates the difference between the means as negative 0.235. The third line of text tells us about the confidence interval. 95% confidence interval is defined by the confidence bounds of negative 1.450 to 0.980. If we do an analysis comparing samples from 2 or more populations or processes, we can produce confidence intervals for the mean or other statistics of each sample. Key to understanding number 3 says, confidence intervals which do not overlap indicate a statistically significant difference. However, the converse is not always true. In fact, confidence intervals can overlap by as much as 25%, and still there could be a statistically significant difference. If the confidence intervals do not overlap, then the observed difference is statistically significant. And if hypothesis tests is being used, the null hypothesis is rejected because the null hypothesis says there is no difference. In the example shown here, the confidence intervals are depicted graphically. We see that the confidence interval for the first variable, high pressure, does not overlap the confidence interval for either of the other 2 variables, low and medium pressure. So we conclude that there is a statistically significant difference between high pressure and each of the other 2 variables. However, there is a lot of overlap between confidence intervals for the second and third variables, low pressure and medium pressure. So we could conclude that there is not a statistically significant difference between them. If there were a less obvious overlap, we could perform a 2-sample t-test for these 2 means. For much of statistics, the universe of data is a population. For the disciplines of statistical process control, like Six Sigma, which is often used in manufacturing and process industries, the universe of data is the process, and the data are the counts or measurements produced in the process. In processes, outliers can have a big effect on confidence intervals, so we must use control charts like this X chart to ensure that the process is stable before doing any test dependent on confidence intervals. The X chart shows that we see one data point is outside the upper control limit, the UCL. So the process is not stable, it is not under control. And a process that is not under control is being affected by special causes of variation from outside the process. These must be addressed before the process can be accurately analyzed with confidence intervals. And that's it for the second of our 2 videos on confidence intervals. As you can see, the other statistical concepts mentioned in this video have already been covered in earlier videos and in the book. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip of the week, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter and @StatsA to Z.